I'm going to talk about a new approach to software quality called STPA. Most of my work is in safety critical software, where of course quality is very, very important. What we've noticed in quality for safety critical software is that the quality issues have been changing over time. A long time ago, the majority of problems were component requirements violations. And a lot of our techniques today for software quality have been designed around this problem. We've gotten pretty good at it. We're not perfect, but we've gotten pretty good at that problem. Meanwhile, software has gotten much more complex than it was before, and this other class of problem has been growing. This is where you have unforeseen interactions between complex pieces of software and between software, hardware, software, and humans, interactions that satisfy every single requirement in your system and still cause a quality issue. This has been very difficult to address. I think this is probably the most challenging issue we have now in software quality. Let me give you an example. I'm going to talk about the Mars Polar Lander. It's funny that the keynote speaker also spoke about this example. It's a great one. I'll have a little more detail. This was sent by NASA a while ago to Mars. It comes down, the computer deploys a parachute, the computer then deploys legs, then the computer turns on descent thrusters to slow down, and as soon as you land on the surface, the computer uses sensors in the legs to detect a touchdown. The instant a touchdown occurs, the computer must turn off the descent thrusters, right? You see why that is important. You don't want it to bounce up. You don't want it to flip over. Well, here's what happened. We sent it to Mars. During descent, the legs deployed exactly as planned. Nothing wrong here. The footpad sensors, when the legs came down, there was some vibration. Those footpad sensors are designed to detect vibration. That's how they work. The vibration was within the design spec, which means it sent a signal. They were designed to send a signal when the vibration is in the design spec. It sent a signal to the computer as required. Guess what the computer did? The computer did exactly what it was designed to do. It shut off the descent engines immediately, and the vehicle fell to the surface. It impacted the surface at 80 kilometers per hour. The system was designed to tolerate 8 kilometers per hour maximum. The entire thing was destroyed. 110 million US dollars gone. Uh-oh. Somebody made a mistake, and we missed it. I think this is very interesting because every component performed exactly as designed, including the software, but we still had a quality issue. No single component failed. If you went to the software engineers after this and said, "What did you do wrong in the software?" what do you think they would say? They would say, "I'm not surprised by this. The software performed exactly the way I expected it to. That's how I built it to work. This is not a software problem. This is a hardware problem. Go talk to the hardware people. They made a mistake. Their hardware sent a false signal." You go to the hardware people and tell them, "What did you do wrong?" What do you think they will say? "I didn't make a mistake. I'm not surprised by the way the hardware behaved. My hardware was designed to detect any vibration and send a signal. It's exactly what it did. It's what we tested the hardware to do. It passed every test. Did not violate my expectation of the hardware. This is a software problem. You should go talk to the software people why they didn't have better filtering of the signal and why they didn't look at a different sensor." Who's right? Well, they're both right. This is not a component problem. This is a system problem. And that's why we didn't catch it. We did a really good job testing individual components and looking at individual components, but not a very good job looking at the interactions. This is a software conference, so let's look in more detail at the software piece. Here's the flow diagram from the software that was used. This is some error checking. Here's the key to the whole thing. Here we we look at the last touchdown indicator. If that's true and the current touchdown indicator is true, so we're looking at the current value from sensor and the last value. If they're both true at the same time, we say, okay, looks good. We probably have a touchdown, and we set indicator state to true. Okay, if we don't have that, we do nothing. Okay, now down here we have another check. This occurred, by the way, at 2,000 meters, very, very high up when the legs were deployed. Down here we have another check. If the indicator state is true and event is enabled, we will disable the thrusters. Well, event enabled checks how high it is from another sensor. Event enabled only becomes enabled at 40 meters. Looking at an altitude sensor. Well, at 2,000 meters, when this happened and was set to true, event was not enabled, so we have no, and we go back up, and 100 times per second this executes. So at 2,000 meters, all that happens is this gets set to true, nothing else. Comes down, what happens when it reaches 40 meters? 40 meters, error checking. Are we getting an event from the touchdown sensors? No. Do nothing. What's indicator state at this point? It's true. From before. We come down here, indicator state is true. Event enabled is now enabled because we're at 40 meters, and then we disable the thrusters and it free fell. Do you see the flaw? In hindsight, it's pretty easy to find the flaw. This is what NASA did. NASA reused this software on future projects, and they made one change to fix the problem. They added this step, this single line of code, to reset that indicator state variable. It's incredible that that one line of code missing destroyed the entire program. How did this slip through the cracks? How did we miss this during our quality assurance efforts and during our testing? Well, it turns out, how do we do testing? How do we do assurance? We look at the software requirements. They reviewed the requirements. Here they are on the left here. You can go through every single one of them and show that they are completely satisfied by the software that they used. They checked the requirements, they verified the requirements, they tested the requirements, everything passed, and it was true, everything was met. But we had a missing requirement. This is one of the biggest problems we have today. We have very good methods for checking if we've met the requirements. Not perfect, but a lot of methods to do that. Model checking, testing, traceability and other things. But we don't have a very good way to check for missing or incomplete requirements. This is not really news. In fact, the keynote speaker said this too. Fred Brooks, famous computer scientist, says the hardest single part of building a software system is not actually building it. It's deciding what to build. That's the requirements problem. As software has gotten more and more complex, this is what is getting through the cracks. We don't know what to build. Another problem that made this very hard to catch is that we do a pretty good job looking at the individual components. If you only look at the software, you have requirements like this, must react within X milliseconds. If you look only at the hardware, you have requirements like that, sensor sensitivity. If you look only at the processor loading, you have requirements like this. If you only look at hardware testing and software testing, you only do failure-based methods, you look at failures. Well, there were no failures. What happens is we have really good methods at looking at individual components. We do not have very good methods of looking at the interaction. To anticipate this accident, you have to understand the interaction between software, hardware, and the environment. It's really hard to find this kind of problem by looking at one part. We need better methods to look at this interaction if we're going to catch this. That was 20 years ago. We've gotten better, right? We keep having this accident every couple of years. Here's one 2 years ago. We had another one just this year in January. Here's a Hitomi satellite. It was developed by JAXA, of course, very good engineers. We had unexpected software behavior. This was a totally different application. It wasn't going to Mars. But the computer entered a special mode designed to ignore certain sensors. Now it's down to only one sensor on purpose. Nothing had gone wrong with the other sensors. It just went to a special mode, and it happened to go to that mode at exactly the worst time. because the one sensor it was using indicated that it was spinning when it wasn't. Satellite was fine, but the computer believed it was spinning. What does the computer do? Commands faster and faster rotation to try to correct the spin. What actually happens is the computer causes it to spin out of control, and the entire satellite was destroyed. It looks different. The details are different. I'm going to argue that this was exactly the same accident. It was overlooked for exactly the same reasons. I really like the investigation that was done after this. They did not conclude that it was a single line of code. They did not conclude that it was a single hardware sensor or a single human error. Their conclusion was this project was lacking an approach to examine the overall design of the spacecraft. I think that's exactly right. We don't have very good methods of looking at the interaction between many different types of components. Another engineer involved said, we were unable to let go of our usual methods. Used to work 30 years ago, doesn't work today. Every component, if you look at the details, worked exactly as designed. There were no failures. There were inadequate requirements. Now the million-dollar question, of course, is how can we anticipate this early? Well, this is the foundation of STPA. Let's start with a very simple control loop. Here we have the computer providing control actions to try to control some process. What was the control action that was provided? Instead of thinking about failures, let's think about a control loop. Well, we have what we call an unsafe control action that was provided. The attitude control unit provided movement commands in the same direction as rotation. If that ever happens, we're going to have a bad day. We must do everything we can to prevent that. We want to make sure we have requirements to prevent that. Why in the world would a computer do this? It wasn't on purpose. We might look at something called a process model. Process model, if you haven't taken control theory, is basically the controller's belief about the outside world. This is a process that we can apply before we've written all of the software. We can catch these things very early. So what did the software believe when it provided this control action? Well, it believed incorrectly that the satellite was spinning when it wasn't. Aha! Why did it believe that it was spinning when it wasn't? Well, part of the problem was that it had a special mode on purpose. It was required to do this, to ignore other sensors in this special mode. And if that happens at exactly the same time that we have a calibration problem, we're going to have that incorrect process model, and we're going to have the unsafe control action. This is a way, I'm simplifying the process a little too much here, but I want to show you that there's potential to identify this kind of accident early, before it happens, and make sure we have the right testing, the right requirements, and the right design choices to prevent these problems. This is a way to get the accident report before it happens. This is very squarely up in here, both of the accidents we've talked about so far. These are unforeseen interactions where every component, including the software, operated exactly as expected, but the system did not. So what can we do? Let me do one more example. Everyone likes to talk about autonomous vehicles. Google has had a number of crashes caused by their software. Here's one. The car was driving. It was going to make a right-hand turn. The computer was driving the car. When it makes a right-hand turn, it hugs the shoulder on the right. The computer then detected these construction cones. There's a rule in the computer. When that happens, you must merge left to go around the construction cones. So the computer did that, and it merged right into a bus. Now you may ask, well, we have sensors on the car to detect buses. Why didn't it detect the bus? Well, it did detect the bus. The sensors actually worked exactly as designed as well. It detected the bus, but there is a known limitation of those sensors. We are pretty good at detecting objects, not pretty good at detecting the size of the object. Why is that important? It's not enough to know that there is a vehicle there. You need to know how big it is. Think of it this way. If you have a very small car, you need to be a certain distance in front to safely move over. What if that car is very big? What if it is a large bus or a train? You need much more distance to safely move over. So it's important. Well, they don't know. The software engineers knew that information was not available from the sensors. So what did they do? You have to do something. They made an assumption. They used an average size of the vehicle with an average deceleration rate. And most of the time that worked. In fact, it worked for 1 million miles up to this point, undetected. The one case where it does not work is when you have a very, very large vehicle and it's very, very close and you have a situation where it tries to merge left autonomously, which took 1 million miles to encounter this. Can we anticipate this earlier? We can. If we have time, I'll show you more detail at the end of the lecture, but let's just think about it in terms of a simple control loop. What was the control action? There was a control action to merge left when it was occupied by a bus or when you didn't have enough space. Why? Well, there was a process model. The controller believed that the vehicle was smaller than it really was. It used an average value. What was the feedback? Well, the feedback was missing. There was no feedback provided to the software. Very difficult problem. And the assumption made in the software was not the worst case assumption. It was a most likely case assumption, which is not good enough for safety. So we can potentially use this as a foundation. I haven't shown you the method yet. I've just shown you a simple control loop. But we can potentially build a method to help anticipate these problems and check our requirements, maybe generate requirements, generate test cases, and things like that. Again, in the safety world, this barrier is very well known. Requirements is probably the #1 barrier in software safety. Most software-related accidents are actually not due to a bug in the software. As our speaker this morning said, that's not the issue in terms of safety. Most software-related accidents have been caused by flaws in the requirements. Software did what it was told, and we were wrong. Daniel Jackson writes, as is well known to software engineers, by far the largest class of problems arises from errors made in eliciting, recording, and analysis of requirements. So where is our process to very carefully find problems in requirements? We don't really have one. Another problem is, this is the cost to fix a problem versus when we find it. Obviously, everything we've been talking about was extremely expensive to fix. We have a huge number of these happening every day in safety-critical software. But I have good news and bad news. The bad news is we're finding them very late. Most of them are requirements issues, and we're finding them way back here. That's also the good news. It means we have an opportunity to find things earlier. Everybody knows we need to find things earlier. The problem is we've been lacking methods to do this well. That's what I'm going to show you. It's based on something called a control structure model. If we want to find things this early, when they're being injected and not wait for the code to be written, not wait for it to be operating, we need something that works before we have software code. So we're going to use a model called a control structure. Here's the logic behind a control structure. Do not start with something like this. This is too late. This is a detailed block diagram, or it could be a detailed flow chart. This is too late. You need to start before you've built the software. You need to recognize, if you do start late, what you do is you need to recognize that we can group these things together. How do we group them together? There are many different ways, by function, by proximity, by connections, and so on. In STPA, we group them by control. So we say, look, all of these things are ways to move the satellite. They're mechanisms. This is making the decision where to move. That's a controller. We're going to group all those together, and we're going to analyze this directly. The basic control loop, if you haven't seen this before, we have something called control actions to control some process. We have some feedback to monitor the process. Feedback is used to update the process model, what the controller believes about the outside world. And the control algorithm says, based on what I believe, what do I do about it? You can have a flaw anywhere in this control loop, and these flaws affect each other. In fact, you don't just have one control loop in your system. You have many. You have a hierarchy of control in most systems. And this is what we call a control structure. Control is on the vertical axis. It's very, very important to manage complexity. A lot of the accidents we're having are because the software was so complex, we couldn't understand all of it. So we're going to manage complexity by enforcing some order, some structure. That means every downward arrow is a control action. Controllers on the top have control and authority over things at the bottom. Downward arrows are instructions or commands. Upward arrows are feedback, information about what's happening in the environment. In fact, we wouldn't even start here at all. We would say, if we're starting early, all of this stuff that we're building is inside here. Before we build that, or even know if this is going to be safe, we really have to understand how it's going to interact outside of the software world, how it's going to be controlled by the operators, what kind of information it has to provide to the operator. We need to start there and get that right before we dive into the details. And in fact, this is the difference between a component view and a systems view. If you start with a component view, you're going to miss things. There's one thing we've learned in 70 years of safety engineering, that's it. In fact, we could start even higher. The thing we're building is in here. This entire unit might be a ground station that's being used by Joint Command. It's serving a purpose. There may be coordination issues that we need to think about and understand. This is another control. We actually want to start here. Derive requirements on this box. And then analyze this, derive requirements on the software, and then zoom into the software and continue that way. This is meant to be done in parallel with development. Okay, I've just shown you a model. What's the method? Here's the method. There are 4 steps. You start by identifying what are called losses. What are the things you want to prevent? You draw the control structure, that's your model to analyze, and then you analyze it in 2 steps. You start with unsafe control actions, and then you build scenarios. This is the small accident report before it happens. These are the flaws in your system that you have not fixed, whether requirements are met or not. This is going to be your problems. Okay, let's try this one step at a time. Identify losses. We start with extremely high level. We don't start with the software. We start with the goal of the whole thing. This is a medical example. There's a piece of software in here to control medicine for pain relief that goes to the patient. Here's a button the patient can press. We don't start with the software. We start with this. What are we building this for? What are we trying to prevent? We're trying to prevent loss of life because there's an overdose concern, and we're trying to make sure the patient's pain is relieved. The rest of STPA is going to find every way the software can cause these 2 things. For a nuclear power plant, we may have L1. This is going to come up a lot if you do safety. But we don't have to stop there. We can look at other losses. What about equipment damage? What about environmental contamination? What about loss of power generation? Loss can be anything you want to prevent. That's where we start with STPA. Here in automotive, loss of mission, loss of customer satisfaction we can look at. In STPA, the rest of the process will find every way that the software can contribute to these. There's full traceability. You can prioritize these losses. Some are more important than others. And every result from STPA, every requirement, every missing requirement, every software behavior, every test case is traceable to one of these losses. Next, we build a control structure. Let me show you some examples. This is from aviation. We have air traffic control providing instructions to a flight crew. Flight crew provides commands to some automated controllers. We may have autopilot, auto throttle, and others. These provide commands to the physical aircraft processes, and we have feedback coming up. Here's a specific example. If you happen to work in aviation, this may look familiar. Here we have the software in this block: autopilot, flight director, auto throttle. They're receiving commands from the flight crew. We need to understand how the software, we just had an accident because the software did some behavior that was unexpected by the flight crew. Is that a quality issue? Absolutely, it's a quality issue. The reason we missed it is because we had a missing requirement. Adaptive cruise control. We have radar now in front bumper of a car to follow cars in front, and the computer will control brakes and acceleration. Here's a simple control structure we can start with. Here's a driver providing commands to turn on or off the automation, the software. The software can send commands to accelerate or brake. Here is some feedback coming up. We want the rest of the process will carefully analyze these interactions, analyze potential beliefs, control algorithms, and look for missing and incomplete requirements and other problems that you haven't thought of yet. Here's a fully autonomous aircraft. It looks very similar for autonomous vehicles, by the way, and this is being used by about 70% of automakers today developing self-driving cars. With something that looks like this. Operator may specify a mode, mission commander sends next waypoint, trajectory controller sends a trajectory. This is all software in here. That's the control path. We have a feedback path to detect and make sense of the environment. And flaws can be injected anywhere in this path. We need to make sure we have the requirements to control these interactions. Okay, next, we start to identify causes of the losses. What can go wrong in our system? We have to start somewhere, so we start with the control actions. These are the downward arrows. We identify what's called unsafe control actions. The word unsafe means it can cause a loss. It doesn't just mean loss of life. It could be customer satisfaction or some other issue. So we start with a downward arrow, a command, and we consider 4 ways the command could be unsafe. Doesn't matter if you've met requirements or not. We consider all 4 ways that this could cause a problem. A good example is a brake command, either by a piece of software or by a human in a car. If you do not provide the brake command, you can cause an accident, right? If you provide a brake command, but maybe in the wrong situation, maybe on a highway, maybe at an intersection, you can cause a loss. Even if you obey the rules of the road, if you obey every law, every requirement, you can still cause an accident. What if you provide the brake command in the right situation, in an emergency, to avoid an obstacle, but you're too late, 2 seconds too late? That's important too. That's the 3rd column, timing. The 4th column is about duration. You provide the brake command in the right situation, on time, not too late, but you let go immediately. It's not enough. Or you hold it down too long in a highway. You come to a stop. It's not safe. These are provably complete. We identify those unsafe control actions. There's a lot more to the method that I don't have time to show, but I'll give you a reference if you want to read more. One of the pieces of guidance is an unsafe control action is very precise. It has 4 ingredients. The first is the source controller, who's providing the control action. What is the type, provided or not provided? What is the command, and what is the context? They're written this way so that they're machine readable. They're also very precise and unambiguous. They satisfy all of the things we'd like to see in a requirement. And in fact, you can automatically generate your requirements from these unsafe control actions. You can do it by hand as a human, or there are tools available now that will do this for you. And it's very easy. Here's a simple example. If the computer provides a shift to park command while the vehicle is moving, that could be dangerous. That could lead to a loss. What's the requirement? It shall not provide shift to park command. If you don't like the shall not, you can reword it into something a little bit different. But what you get from STPA, from these unsafe control actions, is a full set of requirements. Every behavior that we need to prevent and that we need to look for in a test. You have the shalls, you have the shall nots, you have the timing requirements, and you have the duration requirements. A lot of times these are missed completely, but it's very important to include. In fact, you can generate these, and because these are generated from the UCAs, these are also machine readable, and these can be used to create an executable model of your software before you have written any code. You can simulate it. Okay, finally, we need to identify loss scenarios. It's not enough just to identify what can go wrong here. It's not enough to create requirements on this path. We need to go deeper. We need to understand, even with that requirement, how could it be violated? What could the controller do? What might it believe? What kind of special mode might exist? Can something lie to the software and cause it to violate a requirement that way? We need to examine this. We do that with STPA in the last step, and we generate scenarios. They look like this. controller will cause this unsafe control action because it incorrectly believes X. The control algorithm does not enforce Y because. Incorrect feedback could be received because. These are pinpointed, precise scenarios that show you the flaw in your system. These are used to make a better design, to make design recommendations, and to make requirements on your system, or to check the requirements that you have. You can also use this to create test cases and identify if you're missing any cases. What about human interactions? Very, very important for software quality. I don't think we've given enough importance to human interactions. I understand why. I used to be a software engineer, and I did not care about human interactions. I did not understand everything I understand today. These are so critical to getting software right. The process, I'll show you that in a moment in an example, but the process is exactly the same. You don't need a PhD in human factors to do this. And I recommend software engineers do this. If you're creating this software, you need to understand what the flight crew can do that may be unsafe if you're going to design good software. So you can do that with the exact same process. What are the commands from the human that may be provided, not provided, and so on? We get requirements for the human, but we don't call them requirements usually. We call them procedures. Here are the things the crew needs to follow, or that we're assuming that they're going to follow. Isn't that important? So many times we've had accidents and software flaws caused by software engineers who made a bad assumption about the humans. And then we do one last step. Why in the world would a human do those things? It's easy for software engineers to think, well, they must be stupid, or they must be distracted. Well, actually, many times, we've had accidents caused because the software we created provided misleading feedback or no feedback and made it impossible for the human to avoid those errors. We need to understand that and take responsibility for that problem in software quality, I think. We get scenarios, we get the accident before it happens, and that allows us to make sure we have a better design, make sure we have requirements and recommendations built in. Here's the entire process. I went really, really fast. I'm going to show you an example now in my remaining time, and I'll give you a link to a handbook if you want to read more. Here's the process, the 4 steps. Start with the losses, build a control structure, identify unsafe control actions, and build scenarios. Let's do a short example. Let's study a really simple system. Let's say the entire autopilot for Tesla's automated vehicle. That's not a simple system. But watch how quickly we can do this. This is a project, by the way, done by a couple of students, not done by me. They had about 3 days to finish the project. They did not work for Tesla. They had 0 experience writing software and 0 experience in industry, in automotive or any other industry. They were brand new students. We taught them the process over 1 week. They decided to study Tesla. First thing they did is ask Tesla for some documentation. What do you think Tesla did? Oh, you're MIT? You want to publish flaws in a Tesla car? We will not help you. So the students decided they were going to test drive the vehicle for 15 minutes, and that will be the total source of knowledge about the system. Almost no understanding about how the system works. And their mission was to use STPA in 3 days to find undiscovered flaws in the software. Sounds impossible. Look what they did. This is not perfect, by the way, but I think it's useful to see what you can do in a couple of days. Here's the simple control structure. This is all you need to find very important flaws. The driver can provide commands to turn this on or off. This is the autopilot, the software. The software can change lanes, accelerate and reduce speed, and so on. They didn't label the feedback, minus 10 points. But okay, even with an imperfect model, what can we get? Here are some unsafe control actions they found. They're very simple things. 2, human behaviors that are unsafe, that are very important for building software to understand. And 2, for the software. This one basically says autopilot does not apply the brakes when there is an obstacle. Obviously, that's unsafe. That's important. We need to prevent that. Then we look at causes of unsafe control actions. We use this template to help us identify problems and flaws without even knowing what the software looks like. Here's that same unsafe control action. Software does not apply brakes for an obstacle. Why? Why in the world would software do this? What do you think? What might it believe when this happens? Maybe it believes there is no obstacle. Of course it's not going to apply brakes if it believes there is no obstacle. Okay, but there is one. How can it believe there is no obstacle when there is one? There are some failures that can cause this if the sensors fail. But we know that. We can detect failures. What about a non-failure? Well, if another car moves in the way and we can't see the obstacle, obviously we're going to believe there is no obstacle when there is one. And you can identify scenarios just like this, using this reasoning, work backward, and identify the accident before it happens. The students did this. Here's 2 scenarios they found in just a couple days. This is the same unsafe control action. Tesla software does not provide braking command for an obstacle. It's a little easier to understand this graphically. Here's the Tesla car. Here's a human driver. Here's the obstacle. Remember what we just said? How in the world would the Tesla software believe there is no obstacle? Well, someone is in the way. There you go. There's one way this could happen. Let's think about this. Tesla is driving. There's a car. There's the obstacle. What is this human going to do? Hopefully, you see the obstacle and you steer out of the path. What if there's another car right here? Then what does the human do? Hopefully you look, you see it. Maybe you go faster, maybe you slow down, and then you turn over. There's a delay. There's a delay. So this car may move out of the way at the last minute. This could happen, and the software does not have enough time to stop, causing a crash, causing this UCA. Exactly. This could definitely happen. By the way, this is a little different than a human. As a human, we would look through the glass. If we can. We can see 2 cars ahead. The radar in the front bumper cannot do that. It was never designed to do that. Now, the students found this. They presented this in 2016. Guess what happened a year later? This exact accident happened a year later. Tesla spent a long time trying to fix this in the software. It's very difficult. They found a way to reprogram the firmware for the off-the-shelf radar that they had used to get it to do something it was never designed to do. They got it to steer the radar beam a little bit lower, bounce the beam under the car in front sometimes, and in certain weather conditions, it will bounce back and detect 2 cars in front, but not always. Not a very good solution. If we had identified this earlier, we could have done something much, much better, and it would have cost a lot less. Here's another scenario that they found. This is a human scenario. Why do we care about humans? Let's read this. Driver provides unsafe steering override command when autopilot is engaged. So Tesla is driving itself. The human grabs the wheel, takes control from the software, and crashes into a car. You're thinking, why do I care? That is a human problem. That is a stupid driver, not my problem. Here's why you care. They did STPA to find every possible way the software can cause this human error. Here's what they found. In their 15 minutes of test driving, they found the Tesla car has 2 cameras to look at the painted lines. and it follows the painted lines. What if the painted lines diverge? What do? There is no perfect answer. What Tesla did, the software decides to follow the one on the right. So, if you're driving down a highway and you encounter an exit ramp, the Tesla car will always take that exit ramp. In 2016, when the analysis was done. What else does it do? Well, they noticed it has a fancy camera and fancy software to detect speed limit signs. And when it takes this exit ramp, it will also detect the new speed limit and automatically apply the brakes and slow down. Now let me ask you something. You're driving down the highway. Your car automatically starts to take the exit and automatically slows down. What do? You will probably grab the wheel and put it back into the other lane. Right? Aha! What if there's a human driver behind you? When you do this, and the Tesla software applies the brakes and goes into this lane, where is this car going to be when the human grabs the steering wheel? The car will probably be right in your blind spot where you don't see it. This is very likely. And in fact, this has happened. After the analysis was done by a couple of students, this happened, and it was a nightmare. Here's a quick video. It's not the exact scenario. This is a similar one that was caught on dash cam. This is the Tesla car. Watch what it does. Do you see why it did that? Why did the software drive into the barrier? It's following the line. And if you look at the barrier is angled. It may not be metal, so the radar may not have had a strong return to provide feedback to the software. The software, this is the software doing exactly what it was designed to do. It had a requirement to follow the line on the right. That's what it did. This is a really tricky quality assurance problem, and we have a method for it. I'm going to skip my other examples and wrap up. Come talk to me. There have been many, many more examples. I'll show you our website if you want more information. This has become very, very popular. All of these companies in automotive are using STPA today for exactly this kind of problem. It's not just automotive. It's being used by Boeing, Embraer, FAA, other regulatory industries, medical devices, defense, space, NASA and JAXA are both using this, nuclear, rail, and others. This is all within the last 5 years or so, 3 to 5 years. It's very, very new, and everybody seems to be starting to use it. It is being introduced in 6 different standards in nuclear, automotive, and aviation industry. But I suspect that it's probably very new to you, as it is new to these standards. This is my last slide. If you want more information about any of this, come talk to me. I'll give you my business card. You can also Google STPA Handbook. This is a guide for practitioners. It's a how-to. It's not a standard. It tells you how the method works and how you can use it to find very specific, precise flaws in your system. We have a conference at MIT that is all about the method I just presented. It's in the last week of March. It's free. We don't try to make a profit. You just have to come. A number of you have already told me you were there last year. Here's our website with all of the analyses that I showed you. All of the examples are on our website. And please email me. Some people are afraid to email me. I love to get email from people. Let me know what you thought and if you have any questions. Thank you.